Okay, I think we can get started now. I think nearly everyone that's planning on attending has joined us. So, hello everyone, and thank you for joining today's UMB Institute for Clinical and Translational Research Enrichment Series presentation. Before we begin, I would like to start off by reminding everyone that this event is recorded. Recordings of all ICTR Enrichment Series events are posted on the ICTR website. We will reserve the last 10 to 15 minutes or so for questions. Please add your questions using the Zoom Q&A feature at the bottom of your screen. As you leave this session, your URL will be redirected to a brief survey. We welcome your thoughts on how we can improve our presentations and what additional topics you are interested in hearing about in the future. So please just take a moment or two to complete the survey. Now I have the privilege of introducing our guest speaker, Dr. Romana Vinjamuri. Dr. Vinjamuri is an associate professor with the Department of Computer Science and Electrical Engineering at University of Maryland, Baltimore County, and the director of the Sensory Motor Control Laboratory, as well as the director of the UMBC site for the National Science Foundation Brain Industry University Cooperative Research Center. He is also a visiting scientist with the National Institute on Drug Abuse, and the ICTR is thrilled that Dr. Vinjamuri has recently joined us as an associate director of our informatics core, providing expertise in machine learning and artificial intelligence research. Please join me in welcoming Dr. Vinjamuri in his presentation on synergy-based brain-machine interfaces in human-robot interaction. Thank you, Dr. Vinjamuri.
Thank you, Anna, for that great introduction, and it's a pleasure to be here. Thank you, Dr. Stephen Davis, for also giving me the opportunity to work with you in ICTR in my capacity. Thank you. I'll get started. Okay, are you able to see my screen okay?
Perfect. Thank you.
Okay. Excellent. Thank you. It's a pleasure and honor to be here with you all and giving a talk for ICTR Enrichment Seminar. Thanks for the organizers and the leadership at UMB and ICTR for organizing this talk. So before I begin, I just want to put it out there that you will see a diversity of topics. So I don't exactly know what background you're coming from, but I do want to share this. I don't know how many of you have been to Dubai. The Dubai that we see now, the person behind it is a sheikh that I'm forgetting the name of. But we went to Dubai in 2023, August with my family, and in a tour in Palm Jumeirah, they showed us a 2-minute video where they were sharing how this Dubai sheikh got inspired to build the Dubai that we see today. And the inspiration was that the only inspiration was that when he was a kid, his parents used to take him to beaches and he would build sand castles there. That was it. That was the inspiration for him to build the Dubai that we see today, the castles that we see today there. So with that, I want you guys to listen to my talk with an open mind. Who knows what collaborations this might bring in, what new ideas this might bring in, both ways for you as well as for me. So let me get started. So this talk is about synergy-based brain-machine interfaces in human-robot collaboration. So there's a lot of topics there. One is synergies, the other is brain-machine interfaces, and then there is human-robot collaboration. So while we get into the topic, you'll understand what these are all about, what are these pieces, and how they're fitting in the puzzle. So let me get started with a bit of introduction here, and then we'll take it. So here's a quick outline of the contents of the presentation. So I'm really interested in, and myself in my lab, we're really interested in answering these two questions. how human brain, which is an intelligent controller, controls human hand, which is probably the best available robot in the world, while performing simple to complex movements. These are the same hands that we use when we are reaching and grasping a cup of coffee, or these are the same hands that we use when we're typing or playing musical instruments. So simple to complex movements, we're using these same hands. And the second question that we're interested in answering is how human hand, which is not just a robot, but it is actually a multidimensional sensory motor device, can provide sensory feedback to human brain. And when that feedback is sent, brain is acting as a multi-input, multi-output parallel processing system. And it is able to make sense of all the information that it is receiving, and it is able to synthesize that into commands. So these are the two questions that we are interested in answering. And this is also comes out of my personal motivation for me, because my mother had stroke paralysis, the very hand that taught me how to write, how to draw, that hand that I saw paralyzed for 10 years. So there's some personal motivation that I want to do this type of research. And so these two questions are not only of importance to engineers or roboticists like me, but also of importance to neuroscientists, neurologists, neurophysiologists, etc. So that's why I think this problem, this human-robot interaction, I think these are of equal relevance to you guys as well in School of Medicine. So these are the two questions, and to answer these two questions, and this is a quick video that I'm gonna. Hey, this is I'm sure many of you recognize this. This is a modular prosthetic limb, MPL, from Applied Physics Laboratory. And just by looking at that video, we can tell how complex the hand movements are, how detailed these movements are. And human hand does these movements super effortlessly, while trying to replicate the same movements in robotics, we struggle a lot. Okay, so this is just an example to show that. So in order to answer these two questions, we take two approaches. One is top-down, understanding the neural representations of hand movements. And to do that, we use EEG, electroencephalography. We also use intracranial EEG, and other modalities like electromyography, etc. And another approach that we take is the bottom-up approach, where we are looking at purely kinematics and dynamics of movements, and we're trying to understand the control mechanisms that are involved in these movements. So these are the two approaches that we take, and these two questions and these two approaches, they lead us to two important applications. One is in motor control, and the other is in motor learning. The first one is, can we improve impaired motor control in individuals with motor disabilities like stroke, spinal cord injury, etc.? Also, can we augment motor control in individuals with needs such as soldiers who are deployed in war zones that are carrying heavy equipment, etc.? And then is motor learning. Can we improve neuromotor rehabilitation? Can we accelerate motor learning? So this is the other question that we're interested in answering, is can we accelerate motor learning by using biomimetic control mechanisms? So these are the two applications. These two questions, two approaches, and two applications, they kind of led me to one answer in my career, and that is synergies. Synergies is derived from a Greek word, synergos, which means working together. And I'm sure you have heard of Bernstein. He was the first one to use this in an academic point of view, where he demonstrated that the synergies is a concept. It is a high-level programming principle, and these synergies are like building blocks of movements. These synergies are like building blocks of movement, meaning just like when I'm talking to you, I'm talking in sentences, and these sentences are composed of words, and words are composed of letters. Exactly like that, when we perform movements, our movements are composed of alphabets of movements. So this is what we're interested in. So if we have several movements, we can decompose them into a few alphabets of movement. And then once we have those few alphabets of movement, we can take those alphabets and we can go back and reconstruct these movements. So there are several studies demonstrated, including our own study, but there are several other famous neurophysiologists, kinesiologists that have demonstrated these synergies. One example that I want to give you to talk about the importance or significance of synergies is if you know 12 of 26 alphabets in English language, you can cover up to 80 to 90% of all English words. So those are ATE, ION, HRS, and LDC. If you know these 12, you can cover up to 80 to 90% of all the English words. So using that similar analogy, if we know maybe a few alphabets of movement, we can give back a lot of function, and that could be life-changing. That could improve somebody's quality of life drastically. So that's the hope, and we'll see some of the research that is supporting this. So very quickly, for those of you who have matrix algebra type background, so if these are synergies, 1, 2, 3, you can think of them as two-dimensional matrices. On the y-axis are different joins, and on the x-axis, sorry, it should be here. On the y-axis are different joins, and x-axis is the time scale. And if you're thinking of these as 3 different alphabets, synergy 1, 2, 3, these can be combined at different time points, at different scales. So this is like a weighted summation, and you can get to this type of movement profile. So you could do this by changing different times, and by changing different weights, you can keep getting different types of movement profiles. So by using just 3 alphabets of movement, we can reconstruct several movement profiles. So that is the key message of these models using synergies. So very early in my career, about 2010, 2011, when I was a postdoc at University of Pittsburgh Medical Center, we demonstrated that we could use these synergies, take only 2 brain signals, and demonstrate the control of a 10 degrees of freedom robotic hand. So we showed this in 2010. We published this work, and we also have a patent based on this work. So later on, we wanted to demonstrate how we can represent this model in the brain. We can use some neural representations, and we can possibly control robotic end effectors using such brain-inspired models. So I'm going back to that same equation that you saw in the previous slide. So the coefficients are here in C, and can get a laser pointer. So the coefficients are C, and the synergies are S. Synergies are the waveforms, and the coefficients are the weights, are the selector signals. So this is still a hypothetical model, but we are hypothesizing that the coefficients come from basal ganglia, thalamocortical loops. So these are the selector signals. And the waveforms themselves of the synergies, they are coming from cerebellar thalamus and motor cortical loops. We're still validating this. We're still trying to use different modalities to validate this model. So let's go into the talk after that introduction. So there'll be 2 main topics. One is the from hand to brain, that is the dimensionality reduction and control of hand movements. And the second will be from brain to hand, that is the neural representations of synergy-based hand movements. And after this, I'm going to show you several applications of these synergies, and hopefully we'll close up with some discussion and questions. So the first part is dimensionality reduction in hand movements. So how can we do this? So given this equation, if I ask you to come to our lab and we record your hand movements, that will primarily be this, angular velocities. From just this, you have to get everything on the right-hand side of the equation. The weights, the synergies, the time shifts, everything on the right-hand side. You need to get everything from just this. Okay, how do we do that? So we break that into two steps. One is getting these synergies first, extraction of synergies, and then figuring out how to optimally combine them by using these seeds. So how do we do that? So the first one is we ask our subjects to do hand movements replicating activities of daily living and instrumental activities of daily living. We ask them to perform these movements while we are recording these movements with instrumented data gloves that can record movements. Once we get those movements, we use dimensionality reduction using principal component analysis, or we could use other methods. From all those 100 movements, we're trying to dimensionally reduce and to get to some alphabets of movement. And when we visualize these alphabets of movement, this is how they look like. So you can see synergy 1, 2, 3. So these are at 4 different time points. And you can also appreciate that the first synergies are whole hand grasps. The second the third and fourth are like cylinder grasp, etc. And the last is a pinch. So you can clearly see that the synergies that we are getting from the data also align with anatomical representations of these alphabets of movement, that is whole hand grasp and a 2-finger pinch. If we can give these two synergies back to an individual with paralysis, for example, we can restore almost 80 to 90% of their daily activities. So once we get these synergies, how do we get back to the movements? So that has got to do with the optimal selection of synergies. Let's say this is the movement that I want to reconstruct. We use convex optimization algorithms. So I'm just making this simple with an animation here. Let's say this is the velocity profile that I want to reconstruct. Here's the synergies, here's the coefficients. I can express them in a very simple equation, y is equal to ax. And I can run my optimization algorithm to reduce the difference between the left-hand side and the right-hand side. And that's when we get these reconstructions. And we can see that reconstruction is almost perfect here. And even the visualization, if you see original grasp, and here is the reconstruction, it pretty much follows the reconstruction. So we also used non-linear dimensionality reduction methods, not only linear methods, we also use non-linear methods to see if this can be improved. But we saw that global linear methods and non-linear methods did well in this. Not going to go too deep into those mathematical methods. We also used other methods to compare linear and non-linear synergies. A lot of this work was done by my first PhD students. Very recently, we also looked at combining these kinematic synergies or hand kinematics with muscle activities, and to see if this can improve the representation of alphabets of movement. And that's where this work, musculoskeletal synergies, was done. And we see that if these kinematics are informed with muscle activities, and if we can infuse that knowledge in extracting these synergies, we can actually improve these motor primitives and these synergies in representation of the movements. Not only that, we added dynamics into the hand kinematics. So far, we focused only hand kinematics, meaning joint movements. But then we also, in our recent work, we added contact forces, because that add a lot of information to the act of hand prehension. So we added contact forces as well into this data analysis. So we used something called a grip glove that can give us the contact forces and contact pressures when you're holding some objects. And we can use those to extract dynamical synergies as well. So we saw several different patterns of dynamical synergies that can give us information that even there is a dimensionality reduction. You can use primitives there as well in dynamics, in addition to kinematics. So that is a quick overview of hand to brain. So the next section we'll be talking is about neural representations of synergy-based hand movement. So this is from brain to hand. So I already mentioned that Bernstein defined these synergies as a high-level programming principles. So basically like a puppet show where the strings are coming from the central nervous system and the higher order systems, and the movements or the basic movements are the synergies that are orchestrating the movements at the musculoskeletal level. So if you look at neural representations of synergies, not just us, there are several other researchers who have seen this and proved this using fMRI, TMS evoked movements, transcranial magnetic stimulation evoked movements, and also in scalp level non-invasive EEG signals. So we took that approach of using EEG to see if we can get some brain regions that are involved in synergy representations, or at least we could use these at a system level where we can extract these neural representations of synergies, and we could use them in controlling, let's say, hand robotics or hand exoskeletons. So in order to do that, we understand that there are limitations of EEG. I'm specifically talking about scalp EEG here, not intracranial EEG. So low spatial resolution, and also it's an indirect approach. So we kind of minimize that complicated equation to this as a weighted linear combination. And we used linear regression models to see if we record hand kinematics and if we record neural signals or scalp EEG signals simultaneously. And we could use some training data to train our multivariate linear regression models and see if we can recreate the testing data. So when we did that, we were surprised to see that, and again, we used broadband EEG features, 1 to 45 hertz range. And so using these EEG features, we were able to reconstruct the movements with up to 90% decoding accuracy. So if you see here, so these are the movements, task 1, task 2, task 3, etc. And in B, I'm representing one movement, but listing out all the joints that are involved in the movement. And what we're plotting here is angular velocities. And you see 3 plots in each of these. One is the recorded kinematics, which is the ground truth. The second is in red is the synergy-based reconstruction. So this is purely kinematic reconstruction. The third is neural decoded. So we use these this MLR model and neural decoded weights to reconstruct these movements. So you see that there is significant overlap across the movements, and it gave us a lot of hope that even using scalp EEG, we can get reasonable accuracies. So in continuing this work, so we used another model to replicate potential interfaces for individuals with paralysis due to spinal cord injury or stroke. So for training set, we used kinematics, but for testing set, we ignored the kinematics for those testing set subjects. So we used synergies from the training subjects, and we used those synergies for the testing subjects. Even then, we were able to get reasonable accuracies in reconstructing the movements. So this also says that if you're looking at basic movement primitives, those are common across many of us. But if you look at the higher order nuanced movements, then probably we might differ. But if we're talking about activities of daily living, you and I, we all share synergies a lot, share these alphabets of movement a lot. Okay, so in the next work, we also did motor imagery-based BCI to see if we can decode representations of synergies. And here are the results that we got. Here are the recorded movements, and here are the decoded movements. And there also we saw significant overlap. Again, I do want to temper these results and claims that these were all done in offline analysis over repeated number of trials. So we had almost 40 to 60 trials per task in order to get this type of results, or 90 plus decoding accuracies. So I do want to put that out there. When we try to replicate these models in real time, we face a lot of challenges, and real-time decoding is still a big challenge that we're still currently working on. So with that two topics, hand to brain and brain to hand, now let me jump into this last topic, and that is about applications of synergies. Now that we have seen the brain and the behavior, I want to present some applications of synergies where we have used them, and you'll be able to appreciate more on. So far, this might seem like theoretical results, but in these applications, you'll probably see some of the practical applications and hopefully some connections and collaborations as well. So let me begin with the first one. This is a hand exoskeleton embedded with synergies. So at first, we didn't even want to build this exoskeleton, but then we realized that if we out there in the market, there is only 5 degrees of freedom exoskeleton. And if you want to buy that, it would cost about 40, 50K. And this exoskeleton for us to build, it took about 10K. And this is also 10 degrees of freedom exoskeleton, and we instrumented this with all kinds of sensors that we could use. So this is a 10 degree of freedom soft cable exoskeleton. Synergies are embedded in a microcontroller Arduino that drives the movements of these exoskeleton. There are also flex sensors that track the joint angular flexions, etc. So there are a lot of advantages of this type of exoskeleton over mechanically implemented synergies. So with this, we have the flexibility to change if we want to do functional synergies or anatomical synergies. Anatomical synergies are like whole hand grasp and a 2-finger pinch. Functional synergies would be something like X, Y, and Z. So these are like X, Y, and Z independent axes. This is also a soft glove. You can easily wear it, and it is not that heavy. So primarily, from the engineering standpoint, we are imposing a low dimensional control method over a high dimensional system. So this is a 10 degree of freedom exoskeleton, but we're trying to control this using just 3 synergies. And I'll show you in a picture, in a video in just a second here. And so if we are getting, let's say, 3 independent signals from a brain-computer interface, we can just use those 3 signals, and we can control these 3 synergies, and we will end up controlling a 10 degree of freedom exoskeleton with just 3 signals. So that's really, really important to note here. And let me show you this quick video. I'm going to quickly jump through parts of the video. So here we are trying to control this hand exoskeleton using surface EMG signals and a basic neural network that sends command signals to the motors that are driving this exoskeleton. So this is a benchtop motor unit. There are several linear actuators that are driven by microcontrollers, and these are pulling strings that are able to enact movements at the joint level for this exoskeleton. So I'm going to quickly jump towards the end, where we're trying to show using wireless EMG, we can easily control the movements of this exoskeleton. And it was not that difficult for the participants to learn how to combine these alphabets of movement to get the exoskeleton to control the movements. It wasn't very difficult for them to get this control going. Okay. So that is the first application. The second application is accelerating motor learning using synergies. So in traditional rehab sense, if you see, repetitive practice of a task is used to learn a new motor skill, or that's what is used in rehab as well, repetitive practice. If you look at literature, we see that experience-based learning is better than exposure-based learning. So what do I mean by experience and exposure? Experience is like a book type learning, and exposure is like a Facebook type learning, just to use a quick analogy there. So here we're trying to see in that acute phase of recovery, in that limited 6 months time post-stroke, let's say, what type of rehab can be the best, or what type of rehab is the most optimal to get the best out of the course of time. So for that, we're trying to pitch here that synergy-based repetition training might be better than the task-based repetition training. For that, we did a quick study where we asked, and this is a preliminary study, we asked 3 groups of subjects. One was based on task repetition, the other was based on synergy repetition, and the last group was a control group that did not receive any training. And the task was trying to pose different hand postures in the pattern that is shown in the touchscreen as shown here. Let me get back to the pointer. So on the touchscreen, we would show them different combinations of buttons, and they have to align their hand to these different buttons. So basically, we're trying to get them to perform newer and newer hand movements that they have never experienced in their life. So in order to do this, we split the task space into 2 sets, testing and training, and we use the training movements. We extracted synergies from them, and we trained the synergy repetition group on specifically those synergies. And when we saw the results, we were really surprised that all 3 groups, they showed similar improvements when tested on the same tasks. But when new movements were introduced, only the group that was trained on synergies, they showed improvements. So we are seeing the transference of skills when we're seeing this, that synergy repetition group is able to perform well. So we extended this work to arm rehabilitation as well. So we trained different individuals on arm synergies, and we have put those synergies into arm rehabilitation exoskeletons as well. And continuing this work on motor learning using synergies, we of course realized that this is a powerful tool that can help in hand rehabilitation post-stroke. So we are trying to develop an immersive virtual reality environment where somebody could wear this hand exoskeleton, and we could provide assist when they're trying to track alphabets of movements in an immersive virtual reality environment. So I think I have a quick video to show how we can do that. By using contactless sensors, in this video, if you're seeing on the table, there's an optical sensor that is trying to track somebody's movements. And we can use such movements, and we can train individuals with motor disabilities to follow these hand movement primitives or hand movements. So this tool can be used for traditional rehab as well as synergy-based rehab. So these are some of the ongoing projects. Okay, and in terms of robotics, so if you see, how do we teach new movements to humanoid robots per se? So the classic method to do that is what is called imitation learning. So you go stand in front of a robot, and the robot has cameras to look at you, and it can replicate your movements. It can imitate and replicate your movements. So this is called imitation learning. So this is the state of the art in teaching movements to humanoid robots. But we're taking an alternate approach here, and we're trying to see if we can teach robots alphabets of movement, or the synergies that you saw in the previous slides. If we can put these alphabets of movement in the microcontrollers driving these robots, then they themselves can be trained to learn just like we're learning, just like how we are learning using biomimetic learning based on movement primitives. These robots can also learn by themselves. That way, imitation learning is restricted to a few movements that you do in front of a robot. But by using this biomimetic learning, robots can themselves learn to extrapolate by using the synergies and create newer movements. So that is a big difference, and we published this work, and we are this is part of the PhD thesis of some of the PhD students, and so we're continuing this work in enabling robots to learn biomimetically. And another application is human emotion recognition in human-robot interaction. So emotion recognition we're trying to implement this using multimodal fusion in human-robot interaction. Let me tell you why this is important. So we saw industrial robotics for a long, long time. Industrial robotics used to be these huge robots that are in cages and they're working by themselves. But these days, we see robots that are sitting at our desks and they're working with us in a collaborative fashion. So in this project, what we try to focus on is, let's say there is a person who is working with this collaborative robot, but it is end of the day, stressed out, 9 p.m., and this collaborative robot is holding a hazardous chemical, and it is bringing it near the human partner. If it knows that the human partner is stressed out, it will try to stay away from it, and it will stop bothering, right? So this is the crux of this work. We're trying to develop some tools for this, but still trying to use multimodal brain-computer interfaces in this domain. So one quick way to demonstrate this is you could use gesture to control robots, right? So you can tell the robot to go that way, the robot will go that way, come this way, come this way. But for that to happen, the participant or the human partner should be able to give such commands. But what if he is stressed out? What if he is sleepy and drowsy? What then, right? So in that case, we could use what is called facial emotion recognition. So this is another quick video to show that we could use facial emotion recognition. So this is a very funny video where my PhD student Farshad Safavi, who just graduated, he's trying to pose, and I worked with him for over 4 years, and I could never make the expressions from his face. So it is a big challenge for the computer to make what his expressions mean. So in this case, he's trying to pose happy and sad faces. When he's happy, the robot moves closer towards him and is at full speed. But when he's sad, the robot goes back to a reset position and tries to stay away from him. So this is a quick way to show that informing human emotions is very important in human robot recognition. And we can also control robots directly by using brain signals. And here we are using a P300 based EEG to decode up, down, left, right. And we're trying to use those signals to control this robotic limb Kinova to different positions. So up and down you saw, and we can also do left and right in the similar way. I'm just keeping track of time, so I'm going to move ahead. And one other application, so this is kind of somewhat parallel to my research, and this is a new domain of research that added to my lab. I'm trained as a motor control engineer / scientist, but I was sitting on these tools of brain-computer interfaces. I never realized that I could apply these skills on the cognitive domain as well. But that was introduced to me through this project of emotion recognition in human-robot interaction. So in this project, NUMA, we're trying to develop an integrated system that can help in substance use disorder. So we see that despite several scientific and technological advances in brain and behavior, there are very limited devices out there that can help individuals with substance use disorder. So in this study, we're trying to develop a wearable device, so a wearable neurotechnology that can help individuals with substance use disorder track their symptoms and possibly some type of intervention as well. So this is still a work in progress. We are very closely collaborating with Maryland Psychiatric Research Center and at UMB, I guess, Department of Psychiatry. We have some early results that demonstrate that by using a combination of physiological plus wearable or scalp EEG signals, or individually with physiological signals or EEG signals. We can get decent decoding accuracies where we are trying to decode stress. Because stress is the key to substance abuse. Stress is not only the key to substance abuse, but we also, in our conversations with psychiatrists and clinicians, we realize that stress can also lead to multiple mental health spectrum disorders. So although we started with this device targeting substance use disorder, this can be extended to other mental health disorders as well. The last application that I'm going to talk about is a very exciting project that we are developing, and this is cyberhuman systems for mental health. And we're trying to see if we can do dance movement therapy for neuro rehab. Again, based on my background in motor control, in sensory motor control, we wanted to see if interlimb coordination in skilled movements can be used as a biomarker for mental health. And we wanted to see if we can achieve that using a human-robot collaboration by robot dance partners. We also wanted to see if these dance partners can help in social connection and engagement, if these robots be humanoid robots. So at the core engineering, we are dealing with a lot of human-robot interaction and collaboration principles. But at the application level, this has direct indications to mental health and therapy. In conversation with Deanna Kelly at MPRC, we realized that this could have strong potential and applications in schizophrenia. So we are currently exploring these projects in collaboration with Maryland Psychiatric Research Center. So those are the three different topics of the presentation. Going into the future research, we will be focusing in motor control and assistive devices and motor learning and rehab, and also added to this new theme, cyber physical systems for mental health. And I want to close with some pictures of the Brain Center. So this is BRAIN. BRAIN is an IUCRC, which stands for Building Reliable Advances and Innovations in Neurotechnology. So BRAIN is an abbreviation. And I did not come up with that cool abbreviation, somebody else did. But we're happy to say that we have a site of this Brain Center at UMBC. And these are some pictures from the planning event that was held in 2022. Several of UMB folks attended this event at that time. I think one of them was Neeraj, who we have a lot of collaborations with. And just this past weekend, we had another BRAIN meeting and event, which we were happy to host. And this is a picture from the top left picture is from that dance movement therapy rehab, which we did in collaboration with our dance school as well as information systems. Some more pictures here. We also have a collaborative networking event with other centers like BRAIN. So just very, very quickly, BRAIN is a IUCRC. You can quickly get to it using this link, nsfbrain.org. UMBC is one of the sites of this center. And our focus is cyberhuman systems, which is led by me, big data AI, Nilanjan Banerjee. I'm sure you know some of the folks on this slide. Machine learning and signal processing by Tulay Adali, neuroimaging and stimulation by Faustin Choa, and virtual reality and augmented reality by Don Engel. So these are folks leading these different themes, and we have very close collaborations with UMB, Hopkins, and Kennedy Krieger Institute. So I want to close my talk with a lot of acknowledgements. The first one goes to my outstanding undergraduate, graduate, and also some of these are high school students who have been supporting this research. They are the ones who are doing the research, and I'm showing off in these talks in front of you. So my sincere acknowledgements goes to these students who have been helping us over the years. and also acknowledgements to my great mentors and collaborators. Otherwise, I wouldn't be doing this multidisciplinary research. I'm trained as an electrical engineer. All my degrees are in electrical engineering. My postdoc was in biomedical engineering, etc. So several of these folks some of them are clinicians, some of them are engineers. So several local collaborations at UMBC as well. And thanks to the funding agencies who have supported our research, and I really hope that they continue to do that going forward as well. And also thanks to all the medical centers that have supported this work. And here's my website. If you Google Vinjamuri Lab, you can easily get to it. And I'm absolutely interested in collaborations. Thank you so much for this opportunity. I hope I finished in time. Happy to take any questions. And here's my quick LinkedIn contact if you want to connect with me. Thank you.
That was brilliant, Dr. Vinjamuri. Just really exciting, and it must be exciting work for your students as well to be engaged in this process. Very meaningful and important work that you do. I just want to remind everyone that you can use the Q&A feature, but if you prefer to actually have a discussion, you can use the raise hand feature at the bottom, and we are happy to let you join in the discussion. Don't think I see any questions or any raised hands. So with that, Dr. Vinjamuri, Dr. Davis, would you like to close our session?
Yeah, Ramana, quite incredible work. So elegant, so sophisticated. Thank you so much. Of the three projects that you outlined, which one do you think is closest for prime time?
It's a good question. So it does appear like we're doing a lot of things here. These the dance movement therapy for neurorehab, this just started last year, so we're still in the beginning stages of it. With NUMA, which is our integrated system for substance use disorder and mental health also, this has been going on for a couple of years, and we're now trying to explore an SBIR STTR with a company that is based in BW Tech, which is our technology park. So we're taking a neurotechnology product approach to this. So, but these other projects have been ongoing. We have solid publications. In these, when I'm talking to clinicians, I always hear that some are these projects are related. For example, pain detection and management can be done using the same framework that we used in this project, using contactless sensing, just the cameras that might be in the clinical monitoring environments. We can look at the posture, we can look at the face, and we can use the same framework to detect pain, etc. For some of the clinical environments. So we have solid frameworks to get started if there's a new collaboration, etc. coming through. Yeah.
Really innovative, and just the facial recognition, because having the ability to recognize human nuance.
Yeah.
What does it really mean? Is extraordinary. Well, extraordinary work.
Thank you.
And thank you. And absolutely, we'll look forward to inviting you back for a future update of this very, very exciting work. Yeah, thanks so much.
Thank you.
Dr. Vinjamuri, we do have a question
Okay.
in the Q&A feature. This is from Dr. Ping. Thanks for the talk. Is there any time series data from your research that is publicly available and you encourage researchers to work on?
Yeah, so all our work is mostly funded by NSF and NIDLR, it's HHS, etc. So we can make that data available for you upon request, but we have not posted the data anywhere. But we can make it available for you if it is of interest to you. Yes. Yeah, especially we have this multimodal data for stress as well as the motor control projects where we have EEG and also behavioral correlates as well. So we can make that data available, yes.
I am adding into the chat our link to our informatics page on the website where Dr. Venjamuri some information about requesting if you would like a consultation with Dr. Venjamuri and his team. If you're interested in AI, machine learning, this is an opportunity for faculty that are interested in a research project and would like some guidance on the next steps. This would be a good opportunity for you to access some, brilliant experience and expertise with this. Oh, I think we have. Okay. I think that concludes our questions. And with that, I think we can release everyone and to enjoy their lunch and the rest of their day. And again, Dr. Venjamuri, thank you for such a very informative, brilliant presentation. It's exciting and actually a little humbling to know that there are people that smart out there working on this. Thank you, really.
Thank you, guys.
Thank you, Wanda and Rachel.
Thank you.
Thank you so much.
Bye, everyone.